morning, everyone, and welcome to Antech Controls Engineering Webinar, Designing Laboratory Spaces. This live webinar is accredited for 1 professional development hour. After the event, all those who have attended the live webinar session will receive an email with a link to request the PDH credit. Questions can be submitted anytime during today's presentation using the chat or question function on your toolbar. There are no costs or cancellation fees associated with attending the webinar. Today's presenter is David Enns. David is a business development specialist here at Antech Controls. He has a Bachelor of Science in Mechanical Engineering and has been with Antech Controls for over 7 years. I will now pass this over to David.
Good morning, everybody. Thanks for being with us here today for our webinar on designing laboratory spaces. We're going to spend about an hour today talking through some of the different points in how to design a laboratory and hopefully helping you solve a few problems you might encounter day to day. As Nicole mentioned, please ask questions throughout the webinar. We will have time at the end to address all of those. If we don't get to your specific question, we will reach out after the fact and answer that for you in a one-on-one fashion. So when designing a laboratory, it's important to consider the many different factors in the ventilation system and how they may affect the overall design of the lab. Modern lab design must ensure safety, containment, and occupant comfort, all while striving to reduce energy consumption. Understanding the effects of each of these factors and how they work together will ensure you have a safe and efficient system. So in today's webinar, you'll learn a few things. We're going to work on the basic concepts related to fume hood containment and control strategies to design fume hoods in appropriate spaces. You'll learn about the effects of diffuser and fume hood placement on fume hood performance. We'll cover the cost benefits of implementing fume hoods with occupancy, and we'll identify factors that drive laboratory airflow usage to plan the most energy efficient labs. So today we're going to run about 50 minutes. I do apologize for those of you who were expecting Cole Crisco to be presenting today. We had to make a quick change late in the game here to a different presenter. So we're going to try to stick to the schedule we show here, running about 50 minutes. I apologize if we're a little quick or a little bit slow, but we're going to try to keep that timing pretty tight. We're going to spend about 5 minutes on standards and system design objective. Really, what are our goals? Then we're going to spend about 10 minutes on fume hood controls and how to design those. We'll spend a little bit of time after that on the actual air distribution and room pressurization inside the laboratory. We're then going to cover occupancy within the laboratory. We're then going to talk about thermal considerations. And finally, we're going to spend a bit of time on working through an actual fairly simple example about how to design a lab. Now, with no more ado, let's dig right in here. Most of the information we're going to pull out here today come from a couple of standards, namely ANSI Z9.5 and the ASHRAE Lab Design Guide. The ASHRAE Applications Handbook is also a really great resource when we're looking at these things. We also may reference ASHRAE 90.1 and ASHRAE 110. These are all really great resources. They all cover slightly different parts of the lab, but taken together, they'll help you design a safe and efficient system. We need to remember in a lab what the goal of each device is and what the goal of the lab at large is. Remember, in the lab space, the goal is safety, first and foremost. We need people working in those laboratories, really regardless of the type of lab, we need them to remain safe. We also want them to be comfortable. We don't want them to feel any drafts, and we also want that space to be efficient. But first and foremost, we want them to be safe. The piece of equipment whose job that is first and foremost is the fume hood. We generally call fume hoods primary containment devices. Generally speaking, if your fume hoods are working, your lab should be safe. If a spill or an incident occurs outside of a fume hood, we then have the laboratory itself to help us. But remember, this is a secondary form of containment. The only thing that can protect the actual worker at a fume hood is the fume hood itself. The laboratory doesn't really protect that person. The lab itself will help to dilute the exposure in that laboratory, but it's mostly there, the laboratory and its pressurization, to protect the building at large, to protect the others outside of that space from being affected by that contaminant and that exposure. We also need to remember that thermal comfort is important. It is a consideration in a lab, just like all other parts of HVAC. And this is probably, 1A, B, C, and D, but we also have to worry about energy efficiency. Labs are absolute energy hogs. They're extreme energy users in this business. And if you'd like to save some energy on a college campus or a university campus, for example, labs are a great place to target to save some energy and save some money. Just because they are single pass systems, every CFM we put into that lab will be exhausted. That makeup air can cost us quite a bit of money in the end. We're going to cover some ways to save a little bit of energy a little bit later in the presentation. So let's look at that primary containment device. Let's look at fume hoods. Remember, the job of a fume hood is to contain harmful vapors and gas. It's to contain effluent in that space. Most experiments and chemical reactions and things like that should be performed right inside the fume hood. If that fume hood is working properly, and don't forget, if that fume hood is used properly, generally speaking, the people in that space will be safe. There are a few different fume hood types. Probably the most common that you'll see and the one that most people picture is the benchtop chemical hood, but there are other types. There are walk-in or distillation hoods. There are some specialty hoods like perchloric acid hoods and radioisotope hoods. Chapter 17 of the 2019 ASHRAE Handbook gives a really good breakdown of all of these hood types. I think there's 12 or 15 different types, and it breaks them all down very succinctly and very, very clearly. I do recommend you give that a read if you'd like to know more about the different fume hood types. We're going to cover two different types in this presentation here. The first is the constant volume fume hood. Generally, these will be benchtop type. Constant volume fume hoods are sometimes seen as an older technology, as something that isn't energy efficient, which isn't altogether true. Constant volume fume hoods use an approximately constant volume airflow with a slightly variable phase velocity. This day and age, in 2020, the constant volume should be fairly precise, usually using some sort of high accuracy terminal or a constant volume Venturi valve. We can maintain very accurate constant volume flows. On these constant volume fume hoods, air will have a route to enter the fume hood that opens proportionally as the sash closes and vice versa. This bypass does take a little bit of design work, and it should be designed so that bypass opens progressively and proportionally. Constant volume fume hoods do have a place in this world. The example I like to use is in a lab that's driven by ventilation rate or by thermal demand. Constant volume fume hoods can be well applied. So what I'm getting at here is if your minimum air change rate or your thermal demand require that you have, say, 1,000 CFM of exhaust. If your fume hoods take up only a portion of that, say 500 CFM, then constant volume fume hoods are a perfectly applied product. Basically, in any application where you do not inflate your makeup air numbers, you can and should use constant volume fume hoods. I say that because they're a more simple device. The controls are less complex, which means they're less expensive and easier to set up and maintain long term. Maintenance of these systems and startup of these systems is absolutely something we have to consider when we think of first and ongoing costs. The other type of hood we can look at are variable volume fume hoods, which are basically the opposite of constant volume. There really isn't a full bypass on these hoods. There may be a restricted bypass, meaning there's always some sort of mechanism for air to enter the fume hood, but it won't make up the full amount of airflow you need in the closed position. These are designed as vertical, horizontal, or combination. We'll show examples of those in a moment here. Variable volume fume hoods should be used in basically all other cases. So what I mean here is look at that same laboratory. It requires 1,000 CFM of exhaust. When the fume hoods in this space open up, however, we need more than 1,000 CFM of exhaust. Say we have 4 fume hoods that each open to 500 CFM. We would overdrive that lab and require 2,000 CFM of exhaust if they're all in use. In this case, our fume hoods would be inflating our makeup air number if they're constant volume. This is a really good application of variable volume fume hoods. Now, in that specific example, when the difference is to the tune of 1,000 CFM, it's a fairly simple choice to go with variable volume hoods. In an example, to exaggerate a little bit here, if the inflation was only 1 CFM of makeup air, we would need 1,001 CFM. The decision gets a little bit harder. When you hit that point, it's basically just a calculation on how much makeup air can we save on any given day or any given year. We can calculate what that 1 CFM costs per year. We'll explain that a little bit later. And we can balance that versus the usage of the more simple system in the constant volume fume hoods. It gets a little bit tough when those numbers come closer together, but when it's exaggerated and we're talking several hundred CFM, the decision should be pretty easy to go to variable volume fume hoods. Inside that variable volume category, there are 3 types: vertical, horizontal, and combination sashes. In my experience, the vertical sash hood is the most popular. Horizontal exists. You'll see a few in a facility with lots of fume hoods, and combination sashes are becoming more popular slowly. But you will probably see all 3 in your ventures here. When we look at variable volume fume hoods, we have to understand what each position on that hood is used for. And generally speaking, there's usually 3 different positions that any given sash can be placed in. We're mostly talking about the vertical sash hood here. First, they can be in the fully closed position like the image we show you on the screen here, meaning that sash is closed down as far as it will go. With some fume hoods, that sash won't actually close all the way. It'll have a 1 inch or so opening at the bottom to allow some airflow to go in. Some hoods will close all the way down to a piece of sheet metal. That's usually an airfoil, however, that they're closing down to, and there is a gap underneath that piece of sheet metal that will allow air to pass into the hood. The next place these sashes can be positioned is at the working height. Sometimes that's 10 inches, 12 inches, or even 18 inches open, depending what type of work the user will be doing inside that hood. A certain different opening could be prescribed. Most fume hoods, like the one you see on the screen, can have that working height reset for each individual hood. You could set it to 11 3/4 inches if you'd like to do that. The next position these can be in is the full open position. This is often not a normal operating condition. Some fume hoods will never go to their full open position. So on the hood we're showing on the screen here, those can open to 24 or 30 inches when they're wide open. This is sometimes used for setup of experiments, but oftentimes the mechanical system isn't designed to actually accommodate that full open position, that wide open spot. Meaning you might have a caution alarm going off or an actual true alarm saying you have low velocity and no containment, which is okay for the setup of the hood, but it usually shouldn't be used in the actual operation. To save some energy and to save some equipment costs up front, I really don't recommend designing for that that full open position of 24 or 30 inches, unless we know it needs to be used by the people working on that fume hood. This is where we're going to start to recommend that, interviewing the people using these fume hoods is the best way to find out how to design a lab. Interviewing the person that's going to be dedicated to that fume hood, they'll tell you what chemicals they're using, what sash height they need to be open to. They'll even tell you what type of fume hood they prefer. They are often experts in this field and can really help navigate those decisions and things like that. If you can't get that information, there are some assumptions we can make, but it's always best to get it from the working staff in that facility. Now remember, fume hoods are primary containment devices. They are our first line of defense. So what we need to do with fume hoods is verify that they're actually working. Like most parts of HVAC with test and balance and commissioning agents and things like this, we need to verify that what we do actually works. For fume hoods, we often rely on the velocity of air entering that fume hood. Velocity is the air velocity that's perpendicular to the fume hood plane. So you can see that arrow facing straight into the fume hood. Really, that fume hood's only job is to make sure air goes in that direction into the hood at a certain pace. Now, ANSI Z9.5 breaks this down for us really, really nicely. It gives a range, I believe, between 50 feet per minute all the way up to 150 feet per minute, and breaks down for you what's good, bad, what costs you money, and what doesn't work. And really, it doesn't tell you exactly what to do for every hood. It's not there to do that for you. It tells you in each range what the pros and cons are. Most fume hoods, and this is a very broad statement, it may not apply to your specific hoods you're going to use, but broadly speaking, most fume hoods operate at about 100 feet per minute. It's right in the middle. It's a generally accepted velocity that works for most fume hoods from most manufacturers. Some hoods will work in the range of 80 to 120 feet per minute, and the statement could be made that any given hood could work at 80 or 120. But face velocity isn't the only thing that will tell you that that fume hood is working. There are fume hoods out there that are designed to work at lower velocities. This is often in the range of 60 or maybe even 50 up to 80 feet per minute. It's not always okay to just prescribe that lower velocity. You need to look at the specific hood from the specific manufacturer, and you need to look at the environment it's going to be used in. If it's going to be used in an extremely turbulent environment, more on that later, then those low velocity fume hoods might not be the best choice. Again, look at the manufacturer and look at the data on that fume hood to find out if we can use it at lower velocities. One of the benefits of lower velocities is its lower energy. If you have 5 square feet of open area and you only need to maintain 80 feet per minute, that will be less expensive than needing to maintain 120 feet per minute because we need less air to do that, which means we're providing less makeup air back into the lab. But like I mentioned, face velocity isn't the only thing that will tell us if a fume hood is working. It's actually really the least good way to know if a fume hood is working. Unfortunately, it's the easiest thing to measure on a fume hood. So there's 3 ways to test fume hoods. The first and the most common is a face velocity measurement. For a 4-foot hood, like the example we're showing here, the actual opening will be anywhere between about 38 and 40 inches. Those fume hoods, like I mentioned, can open up to 12 inches or 18 inches. We've shown an example here that opens up to 18 inches. What we would do with something this size is split it into 8 unique areas. And using a thermal anemometer, we would measure the velocity in the center of each of those spaces, and we would average it out. What we would then need to do is ensure that the velocity through any one of those 8 openings doesn't vary too far from the mean. None of them's too high, none of them's too low. Often what you'll see is on the edges, you'll get low velocities, and in the center, you can get high velocities. They're never going to all line up perfectly unless you get that perfect fume hood in the perfect condition. It's the average of these 8 that we care about. That's the easiest way to measure containment on a fume hood, but again, it's not the be-all and end-all. We should also be doing flow visualization tests and tracer gas tests. Flow visualization tests are smoke tests. They can be done in 2 ways. The first is releasing a gas or smoke inside the fume hood when it's opened or closed. What you're looking for here is that the smoke in the air is directly pulled back and up and out of the fume hood. What we want to avoid is lazy airflow, meaning when we release that smoke, does it drift towards the front of the fume hood, towards the sash, before heading out the back? That's what we want to avoid. The second way is to release smoke from the outside of the fume hood, generally in the closed sash position, but also in the open sash position, to make sure, again, we don't have lazy flow and that air moves right into the fume hood. Again, that could happen at 82 feet per minute, that could happen at 101, that could happen at 119 feet per minute. But if smoke generally goes into the fume hood nice and quickly and directly, that fume hood's working pretty well. The last thing we can do, and this is the most involved test, is a tracer gas test. This uses an actual dummy, a mannequin standing in front of the fume hood with a sensing element placed in its mouth directly where you would be breathing. And what this does is it captures any effluent that might escape from the fume hood and will let us review how much of that tracer gas is escaping. And you can set limits on how much containment or how good a containment you can actually need on this hood, and that'll allow you to know whether this fume hood is working for you or not. In an ideal scenario, every single fume hood that is ever installed and started up gets all 3 of these tests performed. In my experience, that really doesn't happen. Now let's start to talk about the control of these fume hoods. Again, we mentioned vertical sash, horizontal, and combination, and each of these will benefit from a different type of control strategy. The most common, as I mentioned in my experience, is the vertical sash hood. Vertical sash hoods benefit from an open loop strategy. If you reference any other ANTEC controlled webinars, you'll hear us use the terms open loop and closed loop quite often. Open loop controls are those that don't directly measure the variable they're trying to control. So for example, if you're trying to control airflow, you might want to measure airflow. That would be a closed loop. If you're trying to control airflow, you might also measure position, like in a Venturi valve. That's an open loop control. The other type of control we can do, like I mentioned, is closed loop. Closed loop control measures the variable it's trying to control. So for us, open loop control is done by sash position sensing. We simply measure the open area and provide the appropriate amount of air using a mathematical equation to get the right face velocity. Closed loop control does the opposite. It measures the face velocity, and if it's low, it opens the valve. If it's high, it closes the valve. Open loop looks just like this. Sash position control is a very simple control strategy. We know the width of the fume hood. It doesn't generally change. And we can measure the height using a sash position sensor. So on this specific hood, we know the sash opens to 18 inches. Maybe it's 48 inches wide. If we divide by 144 to get our units right and multiply by the face velocity target, we now know we need 600 CFM to get that face velocity exactly to 100 feet per minute. Always remember, when we're doing sash position control, while it looks this simple, in reality, it never lines up quite this perfectly. There is some leakage, there is a flow characteristic of that fume hood, and all of that's going to play together to make that 600 CFM be approximate. You always need to balance this flow out. Now, I'm not saying that 600 is going to be completely wrong and you might need to provide 200 CFM. That's not working correctly. But you might need to balance this by 5 or 10% to get it working on your specific fume hood. For closed loop control, again, it's a little bit different. All it does is directly measure the face velocity, and if it's low, it opens it. If it's high, it closes it. This is done on a control loop that can be tuned. So it can be ultra fast or it can be ultra accurate. Generally, you want to find a happy medium between fast and accurate where we can get quick response times, but also maintain that 100 feet per minute generally without too much overshoot or undershoot. There is a third strategy for controlling a fume hood as well. This lends itself very, very well to combination sashes. We like to call this hybrid control. This is what you might describe as both open loop and closed loop. In the end, however, it is a closed loop strategy. What you do with this strategy is employ both sash position sensors and sidewall sensors. Basically, the first movement is controlled by the sash sensor. Anytime your sash is in motion, the only thing in control is the sash sensor. This gives you a really fast, good first guess. So like the example before, we would drive directly to 600 CFM. As soon as that sash stops moving, then the sidewall sensor kicks in and provides basically a tuning loop for us. Maybe 600 was close, but we need to tune that back to 580 CFM or up to 650. Basically, if there's people standing in front of the hood or those horizontal panes of glass open, really anything affecting the hood now, we're still fast, but we're also very accurate in that regard. So there's pros and cons to each of these different three types. Sash sensing is the fastest and it is very, very stable. However, it's open loop. So it doesn't actually know if it created the right face velocity for you, and it does not compensate for obstructions. Sidewall sensing is the opposite. It does compensate for obstruction, so it is very, very accurate. The downside is it will need to tune that loop for you. It is a control loop that will take some time to get it right. It can still be done very quickly, but it won't be as quick as sash position sensing. Then there's hybrid sensing, which again combines the best of both worlds. It's fast and it's accurate, and it's now also redundant. So if one of your sensors fails or if somebody plays with that sash position sensor for some reason, you have the other sensor to fall back on to keep that fume hood working, saving you time and energy. The downside is you now require two sensors, which would have a bit of an impact on initial cost. So now we've discussed the fume hoods at fair length here. If you'd like more information on fume hoods specifically or other exhaust devices in the lab, please go to antechcontrols.com and view some of our past webinars. We do have one dedicated to the equipment inside labs as well. But now I'd like to move on to the actual air distribution in the lab. What air change rates we might use, and what kind of room pressurization are we actually looking at here. For air distribution, this is going to help us maintain proper air movement and direction within the lab environment. Now, labs aren't special in this regard. Whether it's isolation rooms or operating rooms, or small offices or dormitories or hotel rooms, movement of air inside these spaces is important for all parts of HVAC. We just have to remember that doesn't change for laboratories. It's also very integral in the lab environment. We need to make sure we evaluate it on three fronts. We need to look at room air velocities. We need to look at the locations of devices relative to each other. Now, when I say that, I don't just mean one diffuser to the next. I mean one diffuser to the next and to fume hoods and equipment and things like that. We also need to look at our device type. When we're looking at our supply diffuser selection, we have to make sure they're not negatively impacting our fume hoods. We do have some guidelines on this. The ASHRAE Lab Design Guide in Chapter 6, if you'd like to reference it, gives us a sort of metric to use here. And it says below 7 feet, supply air diffuser velocity should be kept below 20 to 50% of the fume hood face velocity. That 20% mark is quite low. Remember, the fume hood average face velocity is about 100 feet per minute. 20% of that is only 20 feet per minute. You'll likely struggle to measure that inside a room using commercially available equipment. The 50% should be fairly achievable. We ideally want to be below that, however. This can be a tough part of lab design. So when you're placing diffusers close to each other or far apart from each other, take into account their velocities and their throw values, and make sure we deal with those collisions in that lab space as well. We don't want those collisions collapsing down on the fume hood and causing extremely turbulent air in front of the hood. Number one, it's going to be uncomfortable, but much more importantly, it will affect that 100 feet per minute heading into that fume hood. ANSI Z9.5 gives us a fairly similar metric, slightly different numbers, however. It states that supply air distribution should be done so that the air jet velocities are less than half and preferably less than a quarter of the capture velocity of the lab hood. So they say preferably less than 25%, but at least less than 50%. Similar, but slightly different than the lab design guide. Oftentimes, we'll have to treat the lab a little bit differently when we actually pick diffusers. The standard 4-way plaque diffuser or cone diffuser may not work for you in these instances. They'll have great mixing characteristics, but they'll often have very high throw values that are not going to work in our lab environment. Now, in saying that, I have personally been in labs that do work with 4-way diffusers in them. I know they're very cost effective and it's a very common look throughout a lot of buildings. It just may not always work for you. We need to select these diffusers to keep the direction of airflow away from fume hoods. Ideally, you can select 2-way or even 3-way diffusers that just aim away from the fume hoods. That may give you higher local velocities in other parts of the room. So in the top example, along those left and right walls there, you might have higher velocities, which might not be as comfortable for occupants, but that fume hood remains safe. There is a happy medium here between all of this where occupants can be kept safe and fume hoods can operate. So don't let me blow this out of proportion for you, but it is something you need to consider for yourselves. When you look at that bottom image there where we put the big red X, this is an important note. Don't take 2-way diffusers or slot diffusers and aim them directly down at fume hoods. Now, sitting here watching a webinar before you go design a lab, it's kind of a simple and moot point to make. Obviously, we wouldn't do that. However, it does happen. Sometimes facilities are built this way. When we teach technicians to start up and commission and balance these systems, we do tell them, if you're working on a fume hood and you're really struggling to balance it and you can't figure out why, look up. Look at the diffusers, and if they're aimed directly at the fume hood, well, that diffuser may have to move. It will cause that fume hood to basically not work and not contain all that effluent. So again, it's easy and a no-brainer right now, but it is something to review in the actual installed and built environment. It can happen. We're going to move on now to air change rates. I'm going to sidebar here over to healthcare for a moment. In the healthcare environment, we're given really good, clear-cut numbers for what minimum air change rates to provide. Operating rooms is a minimum of 20 air changes. Isolation rooms is a minimum of 12 in the isolation room and 10 in the ante room. Whether it's an office, an elementary school, or a university classroom, we're given all sorts of really great numbers here for what to provide for air changes in those spaces to help with safety, thermal comfort, and all of those things. Unfortunately, the lab world doesn't quite work that way. In this world, whether it's with the ASHRAE Lab Design Guide or ANSI Z9.5 or NFPA or all of these other standards, we're given ranges quite often. So specifically, the ASHRAE Lab Design Guide, Chapter 11, if you'd like to reference it, gives us a range of 6 to 12 air changes per hour when the space is occupied. 6 air changes, in my experience, is the most common. You will see some that go up to 8, 10, or 12. Basically, you start to get diminishing returns. The change from 6 air changes to 8 can help with occupant safety. It will dilute those chemicals quicker, and then we can exhaust them safely. The same may be able to be said for 8 to 10, but from 10 to 12 and 12 and above, you may start to see diminishing returns. This is a fairly hotly debated topic. You'll see lots of CFD studies. There's lots of different universities and organizations that are doing studies on this exact number to try to narrow it down. In my experience, they're all saying basically the same thing, that there's not a perfect correlation one way or the other. So the only thing I can really recommend for you here today is anywhere between 6 to 12. The most common I see is 6. Now that tells us about the air change rate, and now we know about the diffusers we're going to select, but how do we actually pressurize this laboratory? It would be unwise for me here to state that all labs are negative. Some spaces like clean rooms and tissue culture and laser labs, some specialized spaces may be positively pressurized. However, for the most part, laboratories are typically negatively pressurized spaces to help prevent airborne pollutants generated in a lab from migrating to the other parts of the building. This also will help us mitigate smells that might come out of that laboratory as well. A typical value for that room pressurization is about 0.05 inches of water. I've seen labs that are 0.01, 0.02, all the way up to 0.05. It depends what kind of containment you need. If you're dealing with a high school lab that needs to be a little bit pressurized, you might be lower than that. If you're dealing with a higher level research style laboratory that has some actual real chemical in it, you might need to be at or above that 0.05 inches. We need to make sure we don't overpressurize these labs so that we don't suck too much air and affect the rest of the building. We also need to make sure that people can actually physically get into and out of these laboratories and we don't affect the doors too much. Generally speaking, however, the goal is to make sure that air goes from a clean space to a less clean space. I don't like to say dirty too much. That is what we show here. Dirty gives a bit of a connotation, but we want to go from clean to less clean spaces. One thing I find extremely useful in the design process is laying out your plan drawings from bird's eye view and just drawing the arrows on it. You don't always need to put the pressurization and the actual offset airflow you need. So it would be nice to see a downward arrow saying, 0.05 inches at 200 CFM of offset. That's great, but it's not always required. It's nice to at least see the airflow direction so that we understand where air is coming from and going to. That's going to help build the environment. It's also going to help start up balance and commission that environment. That way with smoke testing or even tissue tests, we can make sure air is going in the right direction at all times. The pressurization number is important, but the pressurization direction is even more important. So we're about halfway through here. We're about half past the hour. I think we're keeping on time here. What we'd like to talk about now is occupancy for fume hoods. Let's try to start saving some money in these well-designed labs that we now have. One of the easiest ways to save money in a lab is to decrease fume hood face velocity. Now you can't just do this carte blanche. You can't just go ahead and lower face velocity. First and foremost, your facility needs to be okay with it. Secondly, maybe a 1B here. Your fume hoods also need to be capable of it. You can't take a fume hood that only works at 100 feet per minute and just turn it down to 60 feet per minute or even 80 feet per minute. You might be containing no chemicals at that point. So both of those things need to be true. The second thing to remember is we cannot reduce the face velocity when people are working in front of the fume hood. That's when we need to be at the occupied set point, usually 100 feet per minute. However, if people leave the fume hood for any amount of time and they leave it open, we may still be able to safely contain most of that, if not all of that chemical at a lower velocity. This is where occupancy sensors can help us. So in this image, you can see the small black dot or the small black bar above the sash there on the orange top part of the hood. That's an occupancy sensor, or one example of an occupancy sensor. What these will do with an adjustable time delay and an adjustable field of vision is let you know when nobody's there and reset that fume hood face velocity. Now, in saying all of this, it's important to note the safest fume hood in the world is a closed fume hood. The best way to operate a fume hood, to keep it safe and to keep it as energy efficient as possible, is to close it. You and I on the call here today don't have a lot of control over that. Facilities directors have some control over that. The people that have control of that are the end users that work in front of those fume hoods and the supervisors that work with all of these groups. The best way to keep a safe and efficient fume hood is to train people to close it at the end of the day. Occupancy sensors work. There's no problem with applying them. But the best thing we can do is train people to close those hoods. There's a few ways to deal with this. Most fume hood most controls manufacturers, can help you with monitoring sash position. So if you install a sash position sensor or a sidewall sensor, you can get a really good estimation of how open your sash is. You could, for example, pull that at 2 a.m. or 3 a.m. when nobody should be working. If you're seeing a large amount of fume hoods open any given night, you can relay that information back to those research teams. You can tell them exactly how much energy they're expending. That might help them close the fume hoods. I've also heard, on a lighter note, that shaming people works extremely well. Putting up posters and signing sheets about who left fume hoods open. There's a lot of different mechanisms we can use to make people close these fume hoods. It's not just for energy savings. It's for their safety as well, and we need to help them understand that. If all of that fails, the other thing we can do is use automatic sash closers. What these do is look in front of or in the plane of the fume hood sash, and if nothing is there for a certain amount of time, it'll close the fume hood. Now, as a manufacturer, we do not actually make these devices. They are often third-party devices, or most fume hood manufacturers can offer you these for their standard hoods. The studies I've seen and the reports I've seen on these is they can pay themselves back in about 1.5 years. Standard life of a fume hood is 5, 10, or 15 years. You're going to have energy savings from that automatic sash closer after 1.5 years, and people will be kept safer. To my understanding, Title 24 in California is being updated that fume hood dense laboratories, and it does give a definition for that, are going to require automatic sash closers going forward, just to take the question of this all out of it. The other way we can help save energy in a laboratory is by reducing the minimum fume hood flow. So remember, when a fume hood is open, it's got 6 square feet of open area. It needs about 600 CFM to achieve 100 feet per minute. You saw that calculation earlier. However, that doesn't tell you how much air to provide to the fume hood when that sash does get closed. A fume hood should spend most of its life actually closed. So this is a very important number for us. ANSI Z9.5 gives us a good estimate and a good range. What it states is that the minimum fume hood flow rate should be in the range of 150 to 375 fume hood air changes per hour. To estimate that for you, a standard 4-foot hood takes about 80 to 90 CFM if it's going to use 150 fume hood air changes per hour. Now, we still need to make sure that we're containing all that chemical when the hood's closed, but if you are, you should drive closer and closer to that 150 fume hood air changes per hour. Why is this so important? Remember, every CFM we exhaust costs us money. The estimation in ANSI Z9.5, depending on your market and your design for your mechanical equipment, is a single CFM costs between $3 and $9 per CFM per year. The average is about 5 from what I've seen, meaning if we can reduce a fume hood from 100 CFM down to 80, we can save 20 CFM per hood per year. Multiply that by $5 per CFM, and there's an absolutely massive energy savings to be had here just by reducing that minimum flow. So we're going to quickly breeze through here through the thermal considerations, and then we're going to move into our design example. Just like every other space in HVAC, we do have to concern ourselves with thermal loading. We do have to concern ourselves with occupancy, but most importantly here, we have to concern ourselves with equipment loads. Labs are a space where you might get extremely high density equipment. Notably, refrigerators are going to be one you have to deal with. They can be in the thousands of BTUs that you have to condition, and they might operate 24/7. So you might encounter a laboratory that is actually driven by its thermal load. You might encounter a laboratory as well that's driven by its minimum air change rate. Or you might encounter a lab that's driven by the fume hoods. But very commonly, you'll encounter a lab where that driving factor changes minute by minute and hour by hour. It can go from thermally loaded to driven by ventilation to driven by the fume hoods, and it can change all day, every day. This is a hard part about laboratories and something we're going to deal with in this design example we're doing here. We're going to spend about 10 to 15 minutes on this example. Then we're going to be right at the finish of the webinar here, and then we'll open the floor up to some questions. We're going to design a lab that might be familiar to some of you on the call. This is the laboratory we have here in Winnipeg at Antech Controls by Price. We use this laboratory to demonstrate how labs work and help technicians start their product up. So we're going to walk through a fairly similar design to that layout right there. Some assumptions and considerations for this lab. We're going to use a quantity of 6-foot wide variable volume fume hoods. Our lab is 25 feet wide by 25 feet long with a 10-foot ceiling. And we're going to use a minimum air change rate of 8 for this lab. For whatever reason, our facility doesn't want to go down to 6. We're going to use 8. All right. Lastly, our supply air temperature will be 55 degrees Fahrenheit, and our room set point will be 75 degrees Fahrenheit. So remember, our ventilation rate for this lab can be driven by any one of 4 factors, and this can change throughout the day. We need to make sure we're providing enough airflow to our fume hoods in the opened and closed position, so we can be driven by primary containment devices. We also have to worry about the dilution and displacement of contaminants. This is our minimum ventilation rates. For us, that's 8 air changes an hour. We also have to worry about the control of the thermal and psychrometric environment. We have to deal with those thermal loads and those occupants. And finally, we have to make sure the space is pressurized. Our lab is going to be negatively pressurized. So let's start to put some numbers to this. Number one, how do we deal with that equipment? We have 6-foot wide hoods. The actual width on a 72-inch hood is 64 inches wide inside to inside. They have a depth of 24 inches, and the internal height is 4 feet. When you calculate that out, you get an internal volume of 42.67 cubic feet. Now we're going to assume the minimum hood air changes per hour will work for us. So 42.67 cubic feet at 150 hood air changes per hour gives us 107 CFM at the minimum position. So we can never go below that on the fume hoods. There's 6 of them. When you calculate it out, we need 640 CFM always being exhausted from this laboratory. Let's look at the second issue here, our minimum air change rate. Remember, our lab's 25 by 25 by 10. We're using 8 air changes. So if we calculate our room volume, multiply by our minimum air change rate, divide it by 60 to get our units correct, we're going to need a minimum of 835 CFM. Now, a negatively pressurized space has its air change rate determined by its exhaust. The same would go for healthcare. So this is an exhaust number in our case. The supply would be lower. Third, our thermal loading. In this example, we have a few occupants that total 250 BTUs. We have a lighting load of 5,000 BTUs. Our refrigeration equipment is fairly large at 6,800 or so. We do have a solar load to deal with of 3,000 BTUs for a total of 15,120 BTUs. So there's a few ways to calculate what our minimum supply airflow would be, but using the equation at the bottom there, if we take the thermal load of 15,000 divided by the specific heat and density of dry air, for us, we'll assume that's 0.075 pounds per cubic foot and 0.24 BTUs per pound degree Fahrenheit. We're going to multiply that by the difference between our supply air and our room temperature. For us, that's 75 minus 55 degrees, giving us a 20 degree Fahrenheit differential. Then we're going to multiply that by 60 to get our units right. At minimum, we need to provide 700 CFM at peak thermal load condition. Not a huge change from the other ones, but something we'll have to consider. The last thing that can affect these airflow rates is room pressurization. There's a few ways for you to estimate this as a design engineer. The best way to know this is to build the room, install all the product, and find the right number. But about 6 months to a year before that, you'll have to actually estimate this for people. You can estimate it a few different ways. You can use a certain percent of supply or exhaust air. Commonly in the lab space, it's about 10 to 20% of your supply airflow rate, or your exhaust airflow rate if you'd like to use that. Or you can estimate it based on the number of doors. The healthcare standards and the lab standards all kind of line up here, and they give you an estimate between 75 to 150 CFM per door, depending on the door size and type and whether it's a double sliding door, things like that. I personally like to use about 100 to 150 CFM per door as an estimate, but it is just that, an estimate. That will be changed on site to get us to the right pressurization. For this example, we're going to assume this lab is a little bit leaky, it's slightly older construction. We're going to need 200 CFM of offset in this space. So let's put that all into a table. So when everything's driven to a minimum, our hoods need 640 CFM of exhaust airflow. Our minimum air change rate of 8 air changes requires 830 CFM, and our thermal load requires 700 CFM of supply air. Our pressurization requires an offset of 200. But what about our maximum conditions here? We always have to worry about this condition in the fume hood laboratory. Our hoods open to a height of 18 inches with a width of 64, as mentioned before, and we're going to target 100 feet per minute for the face velocity. To find out approximately how much airflow each of those will need at the maximum position, we can multiply the width times the height of that sash, divide it by 144 because we are in inches and we want it to be in feet, and multiply by our face velocity of 100. What we find out is we need 800 CFM per fume hood at the maximum open position. Meaning if all 6 hoods are fully open at any given time, we need 4,800 CFM of exhaust air from the flow from that lab. Now we're not going to do it in this example, but something you can do as a design engineer is work with the actual end users of this space and find out if they're actually ever going to use all 6 hoods at once. In this laboratory, it would be silly to leave it at 4,800 CFM. We only have 2 occupants. If they're using the lab correctly, the most number of hoods they should have open is 2 at any given time, which means we likely don't need to design for that full flow. We can include some diversity, which will save us on the sizing of our equipment and our ductwork and our air valves. We'll come to that in a moment. So now that we have all these end conditions of minimums and maximums, let's actually look at this. We're going to look at minimum air change rate with our hoods closed and maximum air change rate for thermal loading with our hoods open and closed as well. So in the first condition, with minimum air change rate and our hoods closed, we need a total of 835 CFM of exhaust air. Remember, we calculated that earlier, meaning with a 200 CFM offset, we need 635 CFM of supply air. When thermal loading kicks in, we're going to need to up that to 700 CFM, meaning we're going to have to ramp up our total exhaust. When we actually open those fume hoods, they're going to start to drive our laboratory for us, however, meaning we'll need 4,800 CFM of exhaust, which means our supply has to open up to track it to 4,600. Let's put this in a slightly easier to read format. At the minimum air change rate with our fume hoods closed, we need 630 CFM of supply and a total exhaust of 835 CFM. To split up the total exhaust, our general exhaust will be at 195 because our fume hoods must be at 640 CFM. We calculated that earlier. When we move to the maximum thermal load condition with the fume hoods still closed, our supply has to open up to 700 CFM. Now in this example, we don't have a ton of load to deal with, meaning there's only about a 65 CFM difference between the minimum and the maximum thermal loading condition. You may choose to just design around this 700 CFM to keep your design a little bit more simple. But in this case, we'd have to exhaust a little bit more air and ramp our total up to 900, meaning our general exhaust has to open up because remember, our fume hoods cannot move. They're still at minimum and still at 640 CFM. Now when the hood's open, the lab is driven absolutely wild. Our supply has to open up to 4,600 because our exhaust is now at 4,800 CFM and we must maintain a 200 CFM offset. So how do we actually select air valves for this laboratory? What we've done here is pulled together the minimums and maximums for each valve into a table. Our supply goes from 635 to 4,600. Our general exhaust should go from 0 to 260, which is a little bit odd and we'll cover in a moment. And our fume hoods, remember there's 6 of them, they need to go from 107 to 800. Our supply valve is best served by a dual body 14-inch medium pressure Venturi valve. That can flow between 400 and 5,000 CFM, giving just enough room on the top end to allow us to do some balancing. We're not really approaching that 500 CFM limit, so this makes this a good valve selection. Our general exhaust is best served by a single body size 8 medium pressure Venturi valve. Look at that valve, however. The minimum on it is not 0, it's 35. We could serve this lab with an actual shutoff valve, but that might add some complexities to our sequencing. You'd be best off using a standard body Venturi valve, which has a minimum of 35. This will affect our balancing table that we showed before. We're going to come back to that. Our fume hoods are best served by a single body size 10 medium pressure Venturi valve that can go between 50 and 1000 CFM. Now in this example, I've assumed that the Venturi valve technology is best for our laboratory. If you'd like more information on why we made that decision, we won't be able to dig into it here today. But again, reference antechcontrols.com for our past engineering webinars for airflow control devices. We still offer PD credits for those, and they'll provide a full hour of learning on why we would have picked that technology here. If we go back here to our balancing table, that general exhaust valve has had a bit of an effect. So because it can't close down to 0, it has inflated our makeup air numbers a little bit here to 4,635 CFM. Now our lab, we still have to look at our fume hoods and how we're going to control them. For this laboratory, and this is the real example here in Winnipeg, we do have 3 combination sashes and 3 vertical sashes. Combination sashes could be served by just a sidewall sensor, but we recommend they're served by a hybrid control strategy. For the vertical sashes, those are best served by just a simple sash position sensor. We also may want to include occupancy in this design for reasons stated earlier. Remember, 1 CFM can cost between $3 and $9. We've assumed for our laboratory it costs us $5 per CFM per year. Our fume hoods are left open at 18 inches and our sash width is 64 inches. When people are at the hoods, we need to be at 100 feet per minute, but when they're gone and not in front of that hood, we're allowed to reduce them to 60 feet per minute using the specific fume hoods we have here in Winnipeg. So what we can do here is estimate how often those hoods will be left open and unoccupied. In this example, we calculated it's about 12 hours per day, 7 days a week, that people will leave the fume hoods open, and we can reduce that airflow. So in the open position, we need to be at 800 CFM. In the unoccupied but open position, we could reduce that at 60 feet per minute to 480 CFM. If a single CFM costs $5 per year, and what we're saying here is they're only unoccupied and open for half the year, that single CFM we could estimate then costs us $2.50, meaning we would go from $2,000 to a cost of $1,200 on a single fume hood. For all 6 hoods, if this schedule holds true, there's this cost difference of $4,800 in this lab per year. That's one single lab. If you've got 20 of these and the fume hoods are unoccupied more than ours but left open all the time, there's an absolutely massive savings to be had by reducing from this $2,000 per hood to a lower value. Now, with that, I know we moved through that example fairly quick. We will be sending these slides out after the webinar here when we send out our quiz and things like that after the fact. Thank you all very much for your time. The floor is open now for any questions you may have. We're going to mute ourselves for about 30 seconds to a minute to allow some questions to come in. If we're not able to get to your question in the time allotted here, we will respond to you after the fact. All right, we do have quite a few questions coming in here today, which is really great to see. We unfortunately won't have time for every one of them, so again, we will reach out to you after the fact if we can't get to it today. A great question we got, however, are what are the downsides to increasing the face velocity above 120 feet per minute of a fume hood other than using more energy? So first and foremost on this question, you did hit the nail right on the head. You do use more energy when you go to higher air velocities. Above 120 feet per minute, according to ANSI Z9.5, we might actually hit a high velocity situation here, where instead of actually containing the effluent inside the hood, what we can do is cause turbulence and vortices to occur in and around the threshold of the fume hood. These are low pressure zones that can allow chemicals inside the fume hood to escape out. So not only are we using more energy, but we've created a less safe fume hood. That doesn't always happen above a certain given number, but it is something that there is potential for on any fume hood with high velocity. Another good question we got is, can you reduce the air changes to 4 in unoccupied periods? The recommendation is between 6 and 12 in the occupied hours. There isn't really great information about unoccupied hours in the lab. Something that's going to cost a touch more in a laboratory, but can have a lot of benefit, is demand control ventilation. If you can measure all the pollutants in that lab and the chemicals in that lab and know that the lab is being kept safe, you can reduce them below the 6 air changes in the occupied or unoccupied modes. That's something you'll have to balance the cost of with your system and how much you'll actually save, but it can be a well-employed strategy. So again, there's quite a few more coming in here. That's about all the time we have here today. I apologize for not being able to get to more. Thanks for sticking with us today. We do host these webinars every second month. So if you go back to antechcontrols.com, we're going to have that next topic online early next week. We will be sending the slides out. We will be sending out the PD credits to everybody who attended today's webinar. Thank you all, and stay safe.